people are looking at us from that for the cameras. Okay. Thank you for coming today. I am Henry Carter. I am the project manager for AS Engineering. This is our final presentation.
Might have to click on the invitation to make it like the active. Yeah.
There we go. So like I said, I'm Henry Carter. I'm the project manager. I'm also the water resource engineer. To my right, we have Carly Sheen, our transportation engineer, Darius Lane, our structural engineer, and Francesco Messina, our environmental engineer. For our County Road 38 Goshen, Indiana project, we have been tasked to reconstruct a portion of the County Road 38 corridor, along with the intersection with County Road 21. We've also been tasked with constructing a two-story visitor center, constructing a wastewater treatment system, along with a stormwater management / treatment system. I'm gonna pass on to Carly for the transportation side of things.
Thank you, Henry. So as Henry stated, I'm the transportation engineer for AS Engineering, and I was tasked with redesigning County Road 38 and County Road 21 to accommodate all roadway users, like people who drive vehicles, cyclists, and pedestrians as well. I was tasked with realigning County Road 38 with a 3-lane section along the western portion of the roadway with multi-use path along the stretch of County Road 38 extending on the north and east side of the roadway. I also was in charge of designing the proper parking facilities for the new visitor center that Darius was tasked with designing.
Awesome. You're this way?
For the design constraints, the design vehicle and design speed came from my technical advisor, and the speed was 45 miles per hour, and the vehicle was a WB 67. For my maximum and minimum grade, I got those from the Indiana Design Manual Figure 53-2, and that was a minimum grade of 0.5% and a maximum grade of 4%. For my minimum curb radius at the intersection of 125 feet, that came from the NDOT Figure 46-2. And for my minimum curb radius for my horizontal curve, that was 587 feet, which came from the AASHTO Greenbelt. For my typical section, I went with an HMA normal crown with 12-foot lanes and a 12-foot paved shoulder that drains towards the roadside ditches. For the HMA normal crown for the mainline pavement, I had 1.5 inches of surface, 3 inches of intermediate, and 6 inches of base. For my paved shoulder, I had 1.5 inches of intermediate or surface and 3 inches of intermediate. Then for my roadside ditches, the water resource engineer, Henry, and I designed our roadside ditches for IDM standards with a 4-to-1 slope. For the intersection, I went with a 4-way signalized intersection with dedicated channelized right turn lanes across each approach, with the 10-use multi-use path on the south side of the roadway that extends on the northeast side of the roadway, and also the southwest side of the roadway that will connect to the visitor center that Darius has designed. I also opted for pedestrian refuge islands to make transportation for pedestrians a lot smoother and a lot safer as well. For my radii, I went with radii of 130 feet. On the horizontal curve, I went with an alignment that was pretty similar to the existing alignment of the roadway. And my horizontal curve radius was 730 feet. I also reconnected County Road 38 to Orchard Road on the eastern side of the project. And then you can see the path that connects to the visitor center. For the parking facilities, I opted for 131 stalls that was determined last semester with stall sizes of 10 feet by 20 feet. I also had 6 accessible stalls, all with access aisles per ADA standards. For my maintenance of traffic plan, to ensure that homes and businesses weren't exactly just cut off from this maintenance of traffic, I went with a 2-phase plan. I opted to close the intersection first, and then once construction is complete on the intersection, the eastern portion of the project will be closed to be constructed on. I rerouted traffic to South Main Street up to Plymouth Avenue, and then County Road 40 up to County Road 17. I opted to not navigate traffic down this roadway just to not increase so much traffic around the Goshen Junior High School. For my construction cost, my construction cost came out to be a little over $2.8 million when considering all the necessary factors. I'll now pass it on to our structural engineer, Darius Lane.
Thank you. Yes, my name is Darius Lane and I am the structural engineer for AS Engineering. Pictured here is just the scope and the overall overview for the project. So I was set to design a two-story visitor center that goes relation to the parking lot that Carly designed. So as you can see here is the perfect layout of kind of how it was set up and to match everything as planned and designed. Here is just a 3D render of my overall view and just it gives a basic floor plan that will be pictured in the next slide here. So I was able to get an overall just a little over 40,000 square feet for my design building. The additional outdoor area was exactly to be measured out to be 1,200 square feet. In addition, pictured here is exactly how my layout is, and my covered outdoor area is just to go perfectly and paired with my food court. And overall, that's just kind of how it's set to be. And these were kind of just to be perfect for the masonry walls and the beam layouts, as those were kind of go in comparison, and they vary in size depending on the spacing and the usage of it. So the overall structural framework of it was concrete masonry walls. They each were 10-inch thickness for all the load-bearing walls. The steel reinforcements were actually part of the concrete masonry walls overall. Then they were number 5 rebar at 72 inches spacing. The timber floor support selected that would be best utilized for the projects and to actually support the loads were laminated veneer lumber. So engineer wood would be best for this because as they are a little bit wider spans, and I do have higher ceilings that were set to be at 16 feet per each floor. So the deeper beams needed to be paired that often actually resulted in kind of came to a result from RISA to be doubled beams at the dimensions overall. And so some of them were 12-inch depths, for then those mostly kind of took part in a small section of the roof support. Overall, the beam spans varied depending on the roof in the first floor. So the first floor beam ranges range from 20 feet to 26 feet. But as we got to the roof floor and the beam span ranges, they became as small as 14 feet to 40 feet, as 40 feet being the max due to there was a lot more assembly areas and covered out those wider spans of the beam. So the masonry walls spaced out, they were between a minimum of 20 to 40 feet. The beams themselves were spaced 20 feet apart as they were set. And that was the best thing that kind of came up that RISA designed for. So RISA floor took care of all my gravity loads as RISA 3D took care of the lateral loads. Here for my public occupancy loads, as those were set for both of them, or just mostly the first floor. That was the live load of 100 PSF with a dead load of 10 PSF. And then for the flat roof, it was a live load of 20 PSF. Here pictured is just the result from RISA floor that actually accommodated and worked best for what I had designed for overall. So here you can see that in the red is my masonry walls and how they were spaced out. And then the blue is the beams that RISA came up and designed for. So anything that is kind of 2 here are those 3 numbers with the dash. That means that they are kind of triple beams. So in order for this to actually have worked with the engineering lumber, as lumber by itself is not always the strongest, but in order for it to accommodate, they had to double up. So that's how I designed them instead of just trying to find maybe some timber joist or anything like that. So I stuck with beams and designed it out to just be doubled up in that sort. So it only came to be triple beams when it came to the roof loads. Those were the heaviest loads to be exact. But everything else was able to just kind of stick to double with only a small section being singles. Here, I just demonstrating the area load definitions here. So for the first floor, it's just the basic public occupancy loads as there was that gallery I had here and anything of that. And then obviously the roof is just sticking to the basic flat ordinary roof load. Here is just demonstrating the composite decking loading that I kind of chose overall. So the composite decking was actually going to give me a load of 44 PSF overall too for my design building. My final cost estimate came out to be just a little over $8 million. And I use this using the RSME square foot estimator as it accommodated for everything as far as specific concrete masonry units, as long as the reinforcements and just overall construction costs for the equipment that I would needed to get this kind of put up and designed. And I'll now pass over to Messina.
All right, I'm Francesco Messina. I'm the environmental engineer for AS Engineering. And for this year, I was tasked with developing a wastewater treatment plant for the visitor center, accommodating pre-treatment, primary, secondary, tertiary treatment, as well as disinfection in a disposal structure. This treatment plant must have a flow rate of 1 million gallons per day and use the latest treatment technologies, as well as being in compliance with all local, state, and federal regulations. Figured here, we have the process drawing, just showing the flow throughout the plant. So it goes through the primary treatment or the pre-treatment aspects of the bar rack and perforated fine screens. That continues to the primary treatment of aerated grit chamber and primary clarifier. Secondary treatment of aeration tank, tertiary treatment of membrane bioreactor, and the disinfection of ultraviolet, as well as there being an outfall into the river, accommodated with an end section and riprap. For the pre-treatment, we have the bar racks, which are located outside of the fine screen building. These bar racks have two for redundancy, as most of this plant has two equipment for redundancy. Each equipment can handle the plant on its own. The bar racks takes the larger solids, puts it on the conveyor, and they are dumped into a dumpster where a dump truck can acquire the dump and cart it off. At the end of it, there's a flume. You measure the flow rate through the plant as well as a sampler to make sure everything is in order. According to the water and wastewater engineering design practice and principles, it had a guidance, and these two flow rates are within the guidance. My fine screen building is a very similar loadout to the bar racks, except it is inside, as the fine screens are more available to the weather. So just to protect them, they're inside of a building. The building itself has two skylights that can remove the fine screens when it is time to change them. A similar loadout, except the fine screens have a smaller hole of 9 millimeters just to capture a little bit of the larger solids, but it's not getting as large as the bar racks. It's the same process as putting out a conveyor into a dumpster. And there's two overhead doors on the building to allow the dump trucks to get in, or for the dumpsters to be carted to the outside. But then continues to the aerated grit chamber, which uses a linear motion to make the water and the grit and sand particles flow towards the outlet weir. The flow rate or the velocity is just slow enough for the grit and sand to settle out to the bottom into the grit channel. This also includes a baffle just to avoid short circuiting. Here's just a better typical section picture just to show the flow coming in, as well as the particles dropping to the bottom and then being collected and disposed of. We have a splitter box right after that just to divide the flow into two separate piping. The main pipe is 2.5 feet diameter, as well as the two second pipes being 2 feet diameter. This just allows the flow to be split into two separate primary clarifiers. Here's just a typical section for the primary clarifier. You have the influent coming up from the bottom, coming into here, and as well as it hits the EDI or the energy dissipating inlet just to slow down the flow and allow for the total suspended solids to settle to the bottom. There's also a skimmer arm on the top to scrape up the oil and wrappers and put them in a scum bin, as well as a arm on the bottom to scrape up the sludge and put it in the sludge removal area where it was disposed of. Here's just a better picture to show the sludge discharge pit, as well as the arm that goes along the bottom and the arm that goes around the side, as well as the scum bin right over here. Here's a top-down view just to show the diameter and how long each component is. So once again, the flow is coming through the bottom, so it's coming up through here and dispersing all across the area, and along the sides, it gets overtopped by weirs and continues on to the next part. With the secondary treatment, we have the aeration tank. This aeration tank has 64 coarse bubble diffusers that are 4 feet apart. It shows coarse bubble over discrete just for the bubble size to allow for more air to get through, as well as the coarse bubble diffusers won't get as dirty as discrete diffusers. There's a width and a length of 32.5 feet, as well as a depth of 12.5 feet. The section view just showing the diffusers on the bottom with the aeration line and the influent and effluent entrance and exit. This is the tertiary portion. This is the most complicated part of the process. It is split into 3 separate parts: anoxic, aerobic, and the membrane tank. Anoxic acts as a denitrification process, as the lack of oxygen promotes the growth of a certain amount of bacteria that will take the nitrite and nitrate in the water and turn into nitrogen gas and release it. That falls then into the aerobic tank, which is very similar to the aeration tank. And once it gets to the end, there's 2 in-series membranes, which were the ZWeed 500Ds. The water then goes across the membrane and acts as an ultrafiltration system to trap any remaining suspended solids. Here's just a side view just to show the pumping from the anoxic tank into the aerobic tank and a weir that gets overtopped to flow the water into the membrane tank. For ultraviolet disinfection, I use the Trojan UV 3000 PTP. I have 2 of these in my treatment plant just to accommodate the redundancy, and they have a width of 5 feet, a depth of 5 feet, as well as a length of 20 feet. These blue sections right here are just weirs to bump up the water level to allow the water to collect over all of the ultraviolet lights to make sure every piece of bacteria and virus is disabled. There's another view from the side just to show how the height of the weir. It's about half of the depth just to bump up the water, make sure it comes in contact with all those bulbs. For my disposal structure, this is from Contact, I believe it's pronounced. I selected the 2-foot diameter pipe, and on the right, you can see just the typical cross sections as well as the labeling for each of the things in the table, each of the numbers in the table. My piping plan, I used DIPRA, Ductile Iron Piping Research Association, for a selection of my pipe. From EPA, each pipe needs to be rated for at least 150 PSI. I doubled it just to make sure every pipe is suited for everything. The singular pipes are 2.5 feet in diameter, and each pipe going into a piece of equipment is 2 feet diameter. And the 2.5 feet pipe has 0.5 inch nominal thickness and 0.43 inch nominal thickness respectively. In this, you can also see the piping for the blowers that go to the aeration tank, membrane bioreactor, as well as the pumping for the membrane bioreactor for the RAS and the CIP dosing. My cost estimate, I used the EPA from 1978. With it being such an old document, use the Consumer Price Index from the US Bureau just to accommodate for the money in today's value. As well as for the UV, I use a equation from University of New Hampshire because UV wasn't around in 1978. And that gave me a total cost of $13.35 million. And with that, I'll pass it on to Henry Carter.
Thank you, Frank. So for the water resources portion of the project, we have to focus on 2 things: managing the flood control volume, which is the runoff from the 100-year 24-hour storm, and we must convey that and discharge it into the Elkhart River according to local regulations. And then we have to manage and treat the water quality volume, which that is the first 1.25 inches of runoff of impervious surfaces, and have to reduce the nitrogen loadings by 50% in that volume. To do this, I have 3 stormwater management and treatment BMPs. I have a rain garden, an underground storage area, and I have used SAFL baffles in the storm sewer system. And then auxiliary components are the roadside ditches, culverts, and the storm sewer, which help convey the water appropriately, and I'll be discussing all of these. This is just my design overview of how it's all laid out. From the west flowing to the east into the river, there is roadside ditches, and those flow through culverts right there underneath County Road 21. The building area flows into the rain garden, which will treat for my nitrogen loading, and then that flows back into the roadside ditch and then goes east. All water from the roadside ditch will go into the underground storage system, which will then discharge into the Elkhart River. And then on the east side of the Elkhart River right there, we have the storm sewer system that contains the SAFL baffles and flows west then into the Elkhart River. So this is the rain garden. This collects all of the water volume from the building and parking area. Water flows into the top, and then it flows down through the soil layers. And the top in this nitrification zone, it converts ammonium in the stormwater runoff into nitrate and nitrite. And as it continues flowing through the soil layers, it flows into the denitrification zone, which converts the nitrate nitrite into nitrogen gas, which that just is released into the atmosphere. And the reason this denitrification zone occurs is because of this upturned elbow right there that is at the maximum depth that allows for this to occur. So hydraulics, the water then cannot flow out and it remains stagnant in here. Doing this, I can treat up to 36,000 cubic feet of water, and the infiltration time of the ponded water is 33 hours, which is less than the required 48 hours of it needs to be infiltrated by. Here is a roadside ditch. I will have these on the north and south side of the roadway. They have been sized to in accordance with all of our transportation standards and my needs for the water portion of things. And because of needing to flow through the underground culverts, it has to be a minimum of 1.5 foot of depth. And the flow capacity here is 90 cubic feet per second. Here's a cross section of one of my culverts. I have these on the north and south side of County Road 38, crossing under County Road 21. They're both 86 feet long and are made out of 1.5 foot diameter corrugated aluminum pipe. And the peak flow rate from my runoff is modeled in these blue lines here. That is the water surface elevation at peak flow. Moving on to the underground storage, I have chosen to use our tank storage media blocks. What these are, they're just plastic, kind of like large Legos with extremely high void ratios. You piece them together underneath the roadway or underneath the ground and the roadway in this case. And they have been structurally rated to be able to go underneath roadways and other small stuff on top, such as, gravel and backfill. The peak capacity for my underground detention area is just over 21,000 cubic feet, and the peak storage that will be seen in there is 17,000 cubic feet. On the east side of the Elkhart River, I have the storm sewer system. The reason we went with the storm sewer system is because there's a lot of dense residential area here, and after construction, this will minimize the effect in these areas. On the south side of the road is inlets that will all flow north into the main sewer line. The reason I did this is to save money on materials and construction instead of having main sewer lines on both sides of the roadway. These will be discharged into the Elkhart River through the outlet to the north. And inside of my storm sewer system and some of the catch basins and structures, there are these SAFL baffles. What they do is on the right side here is a lab test of a SAFL baffle. You can see it allows for the solids to settle inside of these catch basins and it stops the scouring. So it acts as a pre-treatment. On the left here is a model that does not have the SAFL baffle, and there's a lot of scouring. The solids that are suspended moving around, and it just reduces the effect that or the potential for settling, and so it just acts as pre-treatment before going into the Elkhart River. Here is a cost estimate for the water resources portion. Overall, all of these came from various sources depending on which one. They're all credible water resources sources though. Overall, the estimate is about $750,000, adding a 20% contingency. It gets to about, which is an additional $150,000. And then rounding to the nearest $50,000 mark for ease of presentation, the total water resources cost is about $900,000. And then after that, for the total project design and construction cost, the $150,000 design cost, which we discussed last semester, and then all of our combined construction costs brings us to about $25,450,000 total project cost. That was our presentation. Any questions?
Mary, I've got a question. The aluminum corrugated metal pipe,
Yes.
why did you choose aluminum?
So I chose aluminum mostly because I found an EPA document when I was looking for culvert design, and the three options that the document was studying was corrugated aluminum, concrete, and then steel. I didn't think it made sense to use steel. I don't know if I've even seen that. And then I just felt I'd use corrugated aluminum pipe instead of concrete pipe, because when I was designing the culvert and Manning's equation, this the Manning's roughness coefficient, it had a lower roughness, so it allowed for a little bit increased flow velocity for using the HY8.
You think it's worth the additional cost? I mean, it's pretty expensive.
I think it is.
Is there concern of leaching aluminum into the environment?
Do not know. That's something, the document was an older document. They probably didn't have quite the environmental standards at that time, so did not discuss that. I did not consider that. Andre?
And since they are asking, so I'm gonna focus on the quality of the stormwater, so your objective is to reduce 50% of the nitrogen.
Yes.
Or maybe my first question is, what is or are the sources of nitrogen from the building roof and the parking area?
So the sources of nitrogen, those can come from well, atmospheric nitrogen when it rains, but just solids and other particulates from sediments on a roadway, or also plants as it goes through the pervious areas. If there is plant matter or other animal matter such as feces, stuff like that, that will all have nitrogen in it.
Let's follow up. So how long does it take to accomplish nitrification? Because you mentioned like 36 hours, the water is gone, infiltrated.
No, that is the amount of time it takes for the ponded depth, the ponded water to then infiltrate. So this area to then be into the ground, so no mosquitoes can. The actual, this process, roughly 120 hours, I do believe. I forget the exact, but it was over 5 days, and so that's why I feared that it infiltrated.
Okay, and so I did not see anything to say that you reduced the nitrogen by 50%. So do I take your word for it, or so? What measure, if you are to do an assessment or measure in here to say that nitrogen is reduced by 50%?
So I guess I do talk about that a little more in the report, but based on, I have several sources of tests. I have the minimum, I believe it's the minimum, yes, the minimum depth here, that, or the maximum depth that you can have denitrification zone, which is 45 centimeters, I believe, and in soil. And then I have is between 1 to 2 inches per hour infiltration rate, allows for the max capacity of nitrogen removal. And then, so based on that depth and that infiltration time, and then the amount of time that it remains in that layer, while comparing it to some of these studies that had actually measured it, it did fit the criteria, and all those were able to treat up to 65% in lab tests. So I just assumed based on.
Assuming you use these like guidelines.
Yes, yes. So I just tried to mimic what these guidelines were.
There is a question for you. Well, I saw the difference in the price between what Theo presented, like $15 million for almost a similar, very similar structure. And you are at just slightly above 8.
Mhm.
So I need 2 buildings instead of 1, and if you can do that. So where does this difference in the price come from?
I believe the difference in the price comes from the use of timber. Timber is cheaper than steel, as he had steel joist members in mind, so timber is actually cheaper than steel. So that's why I chose that actually for my alternatives overall. So when I used the cost estimator, that gave me a combination of what it would be to use, obviously, timber and overall masonry units. That's exactly what I came up with.
You're not using any steel joists or
No.
building sections?
It's just masonry and timber.
Oh, party.
Very quick one. Henry, you spoke about SAFL. I assume SAFL stands for something, or is it just?
I could not figure that out. Looks into it, the manufacturers, they, even in the why Saffle Baffle section, there's no acronym. There is somewhere, but it is not published for.
I should have talked earlier.
So you wouldn't have any questions for Francesco, just saying. Won't say that, it's not too.
Oh, you did a good job.
That's great.